So Mark Isaacson is a software engineer at Facebook, where he works on improving the developer experience for all C++ programmers at Facebook. And Mark is the author of the tech blog called Modern Maintainable Code, and the address is modernmaintainablecode.com. It's Mark's second code dive. He was here last year, you may remember him. We wanted to keep him away, but we couldn't. So here it is, Mark Isaacson and his Exploring C++ 17 and Beyond. Let's have some noise for Mark Isaacson.
Thank you. Thank you all. They really couldn't keep me away this year. I purchased 5 different bus tickets to get here from Berlin. I don't mean, with stops in the middle. I mean, I tried to buy 5 separate tickets direct from Berlin to Wrocław. The first one, I booked 3 months in advance. That's how badly I wanted to be here talking to you. Well, the next one, I thought I was already here. I booked Wrocław to Berlin. And then the last 3 were, in a panic the day of. That was, I think, 1 day ago. That's how bad I wanted to be here with you all. And today we're going to talk about C++ 17 and beyond, right there on the title. And I want to tell you a little bit about what the structure is going to be. The first thing I'm going to do is I'm going to spend about 10 minutes just enumerating all the features real fast, right? Just a few words each. Here's everything that's coming. I'm not going to give you, depth on every single thing. I can't. There's not enough time. But what I will do is cover 3 things that I think are particularly interesting. 2 of them you get to take home and use right now. That's the top one there, that string view, and the bottom one, if const expert. You can use both of those features as early as C++ 11. Right? And I'll show you how. The middle one is just a brain exercise. So there's this feature, operator dot, proposed by Bjarne Strustrup. It may or may not ever get into the standard, but it's so much fun to think about, and I hope you'll agree with me when we get there. All right, so I promised you a giant wall of features. Here it is. Here's the list. And I'm going to skip some, so ask me questions at the end. But let's start by saying there's this thing, TS. File system TS is our first one. A TS is a group of commits. So I've got the lib fundamentals on the right-hand side. Everything below that is just a commit. The TS is all of those together. So let's start with file system. File system is file permissions. Does a file exist? Stuff to combine paths, all of that stuff. We've got parallelism. This is overloads of the standard algorithm header so that you can say, you know what, I'd like you to just figure out how to run this in parallel. Take my algorithm to find and parallelize it. You can do that. You can also say, run it on the GPU, vectorize as a power that you now have. We've got some annotations you can add to your code. One of them is fall through. It says, hey, when I've got a switch statement and a case and I forgot to write a break statement, I didn't actually forget. Now I have a question for you for this next one, this node discard. I spent a very challenging day once on a really nasty bug. And that bug was I had a lock guard, or rather I found a lock guard in our code, and it was never given a name. Now, some of you, I might hear some faint chuckling. When you don't have a name on a lock guard, it has the constructor get called, and then immediately the destructor is called. There's no critical section. None of our code is protected. Anyone else encounter that bug out in the wild? Show of hands. All right. Not as many as I might have thought, actually. It's kind of interesting. If you ever encounter it, hope that someone has annotated your lock guard class with this next thing, this no discard. It makes that bug impossible. It means that you must do something with the variable. You must actually take an action or store it or let it, have the destructor run at the end of the scope instead of immediately. Saves you a lot of pain. Saves you opening up GDB and saying, I'm in a critical section. Why is my variable changing? You're not in the critical section. Interesting ones here. We have variable templates. This is just making template metaprogramming shorter. We have, let's see, type deduction for constructors. Anyone ever wonder why make pair exists? Like, forget what you know now. Have you ever just wondered, like when you were learning the language, why did make pair, why is that a thing? It doesn't have to be anymore. So the reason it's a thing is it lets you deduce types. So for context, pair, if I want to make a pair of ints, I can say pair spell out int, comma, int, and then pass it 5, comma, 5 to initialize it. I can also just say make pair 5, comma, 5. Don't have to tell it it's ints, it just figures it out. And it was kind of this deficiency in the language where we needed to have a separate function whose only purpose was deduction. Now in C++ 17, no problem, you just say pair 5, comma, 5, it works. All right, we're almost through 17. Structured bindings I want to call out. And I really like this feature. The reason I like it is if I've got a map, no more do I have to call .find and say, the iterator I just got out, .first and .second. First and second don't mean anything. Right? Those are the worst names of anything I've ever encountered in C++. We can very much do better. We could at the very least say key and value, but there's probably something else. If it's a phone book, I want name and phone number. And structured bindings is a way in a single line to give those things a name, to make your code readable, to have it be self-documenting. On to the other side. I'm going to skip a few things. So we've got two kinds of variants. We've got any and stood variant. Any means I'll hold any type you want. It allocates it on the heap. You doesn't need to know how big it is. You can put whatever you want. It holds anything. Variant is a little different. It says, you tell me up front, do you want me to hold ints, strings, doubles? That's it. That's all I'm going to hold, nothing else. And that means it knows how big the biggest of those is and can allocate the memory in situ. We've got optional. Optional is a way of saying, hey, I might return a presentation remote, but I also might return nothing. I might return the absence of a value. And the last couple things that I want to mention here, this invoke and apply, is a way of saying I've got a tuple, I want to take everything in it and call a function as if those were the arguments. So there we go. We made it through C++ 17. There's another giant list. I'm sorry. The fun part is soon, I promise. I promise. We're going to deep dive. We're going to see some real code. Now, some of you might be disappointed that some of these things aren't ready yet. I, for one, am very disappointed we don't already have modules, we don't have reflection, we don't have ranges. They're coming. And I'll just tell you this. If you were disappointed that these aren't here yet, the good news is we've changed the way that the standard is shipped. It used to be C++ 11, they waited until everything was ready. And we all saw how well that worked. It took forever, and we had a lot to learn all at once. And so now they're shipping things every 3 years. Whatever's ready is coming, and a lot of this I think you're going to get really, really quickly. Maybe before the standard even ships. The compiler vendors are awesome these days. So I'll pick some favorites here. Ranges is going to be incredible. Ranges is the second version of the STL. So what a range is it's a pair of pointers. Or rather, sorry, it's a pair of iterators. Right? Today's STL algorithm header is based off of an iterator. And iterators should scare you. If they don't scare you, think about C strings. How many bugs have you encountered because of a C string? That's a topic we're going to deep dive a little bit more on in a few minutes. But all of those same bugs happen with iterators. And the reason is they don't know how big they are. You need 2 of them to do anything useful. A range knows where it is and how much there is to go. And because of that, they compose nicely. And it's just going to be a beautiful thing. So I want to call that one out. That one's going to be amazing. We've got reflection on the way. Reflection is stuff like, hey, what data members does this type have? You can ask that in real code in C++. What functions does it have? What are the names of each of the things in my enum? Right? No more mile-long template metaprograms to do that. Enough of that. Let's just have the compiler tell us. And the last one I want to talk about on this slide is modules. Modules is the answer to all of our compilation speed woes. And I won't go into how it works, but I will tell you this much. I think we're going to see the first step of that in C++ 20, but there's going to be multiple parts. It may be a few years before it solves all of the things you would hope for. All right, we made it. big green check mark, right? We've got 10 minutes through where we've covered the giant list of features. Now I'm going to give you what I think is the fun part. And if you do want me to tell you more about any of those things that we didn't talk about, ask me later. But we're going to dive into 3 things. And it all starts with a bug that goes back, I think, as far as C++ itself, but certainly to C++ 98. I've got 2 compilation units here. I've got a foo compilation unit and a main compilation unit. I've got 2 global standard strings. Show of hands, who thinks they see the bug? All right, small number of people. Anyone feel brave and want to shout out what it is? Just go for it. No one feels brave. All right, I'll be brave. I'll tell you what it is. This is a static initialization order fiasco. Right? It's a bunch of fancy words. It has an acronym, SIOF. Gotta know your acronyms. Here's what's going on. In C++, there are 2 potential outcomes that this program can have. The thing that the programmer intends to happen is that when the binary starts running, kfoo says, okay, I've got to make a string here. I'm going to construct a new one. That means I'm going to call the allocator. I'm going to copy that data out of the static section into my newly allocated memory. And then we initialize kbar. Then we say, okay, time to construct kbar. Let's allocate some memory, look at kfoo, get the data out of kfoo. That is one possible outcome. There's another, a terrifying outcome, and that is kbar is allowed by the standard to be initialized first. kfoo has nothing in it. It's garbage data. We just loaded the program into memory, and oops, kbar is trying to initialize first. And it says, let me look at kfoo, and what happens next is undefined behavior. Is that a surprise for people? Show of hands, is that surprising? If it's not surprising, you've been in this language too long. So, old problem, old bug, nasty bug. Happens with strings, happens with other stuff. I want to back up a step. The reason this happens is kind of interesting. There's a special window of time where these variables are initialized. They're not initialized at compile time, they're not initialized at link time, they're not initialized even after your main function has started. They're initialized in a very special window. That window is between when the binary is first loaded into memory and when your main function starts. There's that window where you kind of mostly don't control that, or at least I assume most people don't think about it, before your main function starts, but your binary is running. And it is because these are initialized in that window that you have that problem. And we're going to come back to that in just a second. I've got good news. The good news is we have tools that can automatically detect this stuff, and we have best practices since the bug has been around that just avoid it altogether. So the tool that finds this bug is address sanitizer. Show of hands. I like asking for hands. Who's used address sanitizer? Awesome. If you haven't used it, go turn it on. It will save you hours of debugging. Like, even if you don't run it all the time, do it once. Just take your code base. If you've got GCC or Clang, I think it's --f sanitize equal address, and you run your binary like normal, it will find things for you. One of them is this. Run it with these special options I've got here at the bottom. It'll find this particular bug, which I don't think it does by default. So that's awesome, right? There's a tooling story here. We can catch this. We don't need humans to know about it. We've also got those best practices. So the way we've fixed this for a long time, maybe you've done this and you didn't even know why you did it, is we just made our string constants C strings. We made them const ** const. Great. And this solves the problem. The reason it solves the problem is, well, now this isn't being initialized at runtime. It happens during the compiling or linking step. kfoo there. That's a primitive type. And the compiler knows how to initialize primitive types while it's doing its compiler linker thing. So we write the string literal into the static section. We just say point at the static section. Awesome. This is the way that we make the bug go away. We moved it from being a runtime issue to just happening before the binary even starts. Now we lost something here. what we gained is correctness. So don't get me wrong. This was the right move. We absolutely should do this instead of using standard strings for our global string constants, because standard strings equals bugs. But what we lost is what the programmer was hoping for. What they were hoping for was no bugs and also the standard string interface. They want to be able to call .size. They want to be able to call .begin, .end, all of these lovely things. And I go back to my bit where I talked about why C strings are unsafe. There was this bug a few years ago now called Heartbleed in OpenSSL. And that bug boiled down to C strings. I don't remember which of the C string bugs it was. It was either they kept track of the length incorrectly, or it wasn't null terminated, or any of another few options that you can have. And it should terrify you that I don't remember which bug it was. Right? That there are so many ways to misuse a C string should terrify you. Right? This is a pain that we have become used to. It's not a good pain to have. So standard strings are awesome because we can trust them. We know that the size is always going to be what we expect. It's always going to be inextricably bound with the data. Can't go wrong. I think you all trust standard string to at least do that. Maybe not more. So I want to have my cake and eat it too. I want both of these things, and in C++17 I get both. There's this new type called string view. And the one thing I think everyone in the community can agree on is that it makes this problem better. I'll talk more about some of the other issues with it a little later, but string views are fantastic. Now, I'm going to break down some of the good parts here. Number one is it happens to be a struct. It happens to know both what the data is and how big it is. You can call .size, you can call .begin, you can call .end. The reason that it doesn't have the issue that standard string does is because, again, no work is happening to initialize these variables at runtime. The constexpr keyword takes care of that. Constexpr means, hey, compiler, I am demanding that you initialize this variable at compile time, at least when it's used on a line like that. And so all of the work to set that up happens during the compile step. Now, the reason it can do that is because string view has a constexpr constructor. The reason the constructor can be constexpr is because there's no allocation. Right? A standard string has an allocator call. You cannot do allocations in a constexpr function. String view does no allocations, so we're good. And I should take a step back and just tell you what a string view actually is. It's a pair of pointers. It's a pointer to the start of some data and a pointer to the end of that data. And what's more, those are raw pointers. A string view will never allocate memory. It will never deallocate memory. It just looks at the data. That's it. So it's kind of our new primitive for dealing with string data, our new way of looking at string data. That's great. Now, some of you might be a little confused at this point because I went from having 3 files to 2 files. Right, a little bit jarring. There is still a foo.cpp if there's nothing in it, so I didn't show it here. Slides only have so much space. You can have as many compilation units as you want. They can all pull in kfoo. There's no bug because the work happens at compile time. I just didn't show it because there's no CPP file. And the reason there's no CPP file is because I changed from using extern, which says, hey, let me give you the initial value somewhere else, because the ODR rule is a thing and we need to do that, to constexpr, I am required to provide an initial value immediately. And so I have to put this in the header. I cannot choose to give it an initial value later. Constexpr and extern are incompatible with one another. Right, so this is just language details, but it all works out. All right, so string views. Why do we like them? They're safe and they're convenient. We can't get the heartbleed bug. We can pass them to the standard algorithms because they've got begin and end. And we've got kind of sane behavior. Anyone else write the bug where you have 2 C strings and you try and do equals equals on them and you end up comparing the address, not the data? I swear there should be more hands. I've taught C++ before. You can't get that bug with standard string and string view. The operator overloads protect you, whether or not you're comparing against another string view or something else. All right, we also get performance. Performance is kind of a tricky issue with string view. It gets a little hairy. I'll tell you why in a minute. When I first saw string view, I had a question in mind, which is, should I stop writing const string reference? Should I just switch over to string view? They both are a way to look at string data. And at first glance, yeah, seems like we should do that. If I've got, let's say, that foo function, I have a const string reference. If I want to pass to that function a standard string, I'm just taking a pointer. That's cheap. If, on the other hand, I want to pass in a C string, I now have to construct a standard string. I am required to do so. I must call the allocator, do an O of n copy operation to pass that through. And this can be very surprising if you have, let's say, a map or an unordered map where the keys are standard strings and your constants are not. Right? That could be surprising. By contrast, the function that accepts the string view. This is a couple of pointers, remember? So if I give it a standard string knows where it starts and it knows how big it is, so it's a constant time conversion. Right? The optimizer might even make it go away. But if I give it a C string, things get a little bit more interesting. C strings, that's the pointer to the start. The pointer to the end, I do need to call a strlen, but at least I'm not going into the allocator. And interestingly, depending on where that C string comes from, that strlen call might happen at compile time. So it might be free. It might be a constant time conversion. So sounds to me like string view's awesome. Here's where things get tricky. I've got a struct widget, and my widget has an unordered map where the keys are strings, standard strings, and I've got a function here where I'm going to take whatever this intermediate thing is that you give me, and I'm going to say, is it in the map, yes or no? And I have chosen to call it with a standard string. If I make that type standard string, then this is cheap. I'm taking a few pointers down the whole path, but fundamentally this is a cheap operation. Nothing surprising happens here. If I make this a string view, my complexity has gone out the window. Here's why. I did a cheap conversion to go from my example code on the left there to passing into the foo function. Getting to the string view is easy. But my map.find only takes a const string reference. It is not allowed to take a string view. So it has to do a conversion back to a standard string. And that conversion involves an allocation that wasn't there when I wrote my code like this. Right, so string view is scary. Because if at any point down the road you touch, let's say, the standard library, you touch third-party code like Boost, and anywhere down the road you need a const string reference, you better be passing const string reference the whole way through. So with that in mind, my big caveat for string view is that I need to explain it. I teach an Intro to the Codebase course at Facebook for C++, and I have to include slides on string view. The reason I have to include slides on string view is because it's a landmine. It's a thing that you can step on that goes boom. Because this, and one more thing that I haven't mentioned so far is, people tend to mess up the life cycle issues. If I, let's say, have a string view and I capture that in a Lambda and send it off to another thread, what if the data goes away? Right? A vector of string views should cause you as much concern as a vector of int star. Right? Very scary, very subtle. People don't tend to realize it. So, string view, bottom line, use them for your global constant strings. That's good. There's very little that can go wrong there. It can only improve your life. But the rest of your code base, be careful. Could be good, could be bad. There's a lot to learn. Now, we're going to take a break from the kind of like heavy C++ stuff you can go use at home and talk a little bit about operator dot. And that reminds me, I do need to mention, you can use string views right now if you'd like to. We've got some compilers that are shipping them with them already. But if you want to use them as far back as C++11, go to any number of open source libraries. Facebook's Folly library on GitHub happens to have something called string piece. It's the same thing. You can start using it right now. So you can take what you've learned. You can change your global string constants today. But I want to dive into operator dot. So for me, this proposal is sheer fun. That is the only reason it's up here today, is because it lets us do really interesting stuff. And I'll show you some practical uses of this in a minute, but I want to show you just some really neat stuff that it does where it lowers the barrier to entry. I've wanted for a long time to make a struct that behaves exactly like an int. And you can do that in old school C++. You can write out the 5 pages of operator overloads and do them one by one to make something that behaves like an integer. But that's awful. It's so awful, I've never done it. Operator dot lets me do it on a slide. So on the right there, I've got an int proxy. I can assign it, I can plus equal, I can print it out. Those all work. And the reason they work is, suppose we're talking about the plus equal. We're saying, hey, int proxy, do plus equal. It says, I don't have a plus equal operator, but let me forward that request to whatever I return out of operator dot. So we return an int by reference, and turns out integers do support plus equal. So we do that on the int ref, and then keep going. And so any operation it doesn't know about, it just kind of delegates it forward. And because I've returned it by reference, we do in fact update the data member in our int proxy, and we get something that behaves exactly like an integer in like 5 lines of code. This is beautiful, right? Start thinking of the possibilities. All right, if you've been wondering, where's the dot? There's a term that compiler writers, language writers like to use. It's called lowering. And it's where we rewrite a piece of syntactic sugar like plus equal into something that the compiler already understands. So plus equal, you can imagine being rewritten as x dot operator plus equal parentheses 5. That is where the dot is. Anytime you see a dot, whether it's for a function or a data member, if the class doesn't have it, it forwards it through. All right, well, we can also do things that are normal, things that are sane, things that just are normal C++ without the operator dot proposal. If I want to then add a toString function to my thing that behaves like an int, I just add one. And when I call it over here, when I write dot toString, x dot toString, I'm not calling operator dot because int proxy just has that. So I don't call operator dot for operations that int proxy already knows how to do. All right, so I saw this feature and I said, great, how can I abuse that? And one of the things I came up with is, well, I can implement contracts with that. That seems like a fun thing to try. So now my goal is, I don't just want it to behave like an integer, I want it to be an integer that must be between 0 and 100. How do we do that? All right, so when I say it equals 1,000, we produce some sort of error. Step number 1 you've already seen. It needs to behave like an integer. So there we go. That's step number 1. And let's break this problem down. If I want to do a precondition, if I want to make it so that before you do an operation, we check, hey, is the value sane? Is it between 0 and 100? Where does the code go? Anyone have an idea? Just shout it out. The constructor was shouted out. That will only tell me that it is within the acceptable range at the point where it comes into an existence. I want to know before I do an operation like plus equal. The suggestion was to overload the assignment operator. That is, without more detail, that doesn't do any better than the operator dot overload. I heard something about static members. So I'm going to just go for it. It goes in the operator dot. So before I forward it through and say, hey, go do this thing on the int, just check, is the int in an acceptable range right now? This is not quite what I wanted back a few slides, right? What I want is for you to tell me that there's an error when you do it, but this will tell me when you do the next thing. So we're building to something here. Well, I can also do end-of-life conditions. So an end-of-life condition is, hey, I'm giving you an integer, you can do whatever you want to it, it can go out of the 0 to 100 range for a while, but when it's all said and done, when it falls out of scope, at that moment, make sure that it's between 0 and 100. So that's easy, we all know how to do that, that's a destructor. And now we get the crazy part. So this is complicated, and so I put some arrows on here. I'm gonna walk you through it. So we start way over here, and this is nice. I can actually walk over here and point at stuff. That's great. So we start with x plus equal 5. And we We say, okay, I've got a bounded int. Bounded int doesn't have plus equal. Let's call operator dot. That returns an impl. And we go over to our impl. That also doesn't have plus equal, so we call its operator dot. And now we have an int reference, and we actually do the operation. So far, it just looks like I've added a layer of indirection. That's how we solve all our problems. Now, if you're paying attention, you may have noticed we're returning int ref of this variable ref, which has an int ref on it, which we get from the constructor, which we get from over here, which is the val in our class. So again, so far, all I've done, big layer of indirection. Now, here's where the magic lies. I am creating an impl struct as part of this forwarding process. I am creating it to live just as long as it takes to do this plus equal operation. It comes into an existence right before you do the plus equal, and it gets destructed immediately after it's done because no one captured it. It disappears after that operation is done. So the destructor is called, and now the end of life of this impl is the end of that expression. And boom, we've got post conditions. Now, this is complicated. There's a reason I put arrows on there, so I always like to do a show of thumbs. How are we feeling? Do you feel like you understand this, or should I explain it again? How are we doing? Awesome. I like to see thumbs up. Great. So this is pretty close to what I wanted. It's not quite there, right? If I do the x equals 1,000 stuff, well, it's going to log an error, but it's still going to be equal to 1,000 when that's all done. I want to actually stop it from being 1,000. So if I print it on the next line, it says it's 10. And by the way, I didn't talk about it previously. The reason I'm now logging an error instead of throwing an exception is you can't throw from destructors. That's why that's there. But you can imagine a better error handling strategy that doesn't fit on a slide. So I want a transaction. I want to only do the operation if the operation keeps it in the valid range. And it's actually not that bad to make this transition. I go from just storing a reference back to the original to storing a copy as well. So the constructor of our impl captures it both by reference and by copy. The operator dot on the impl lets you modify the copy, which we then check in the destructor to say, is what you did to the copy okay? If it is, set it back in the original. And if it's not, then log our error. So we've done it. We have contracts, right? For me, this is fun. So some things I'm not going to really talk about that much, but I just wanted to give you more perspective on what operator dot does. If you are familiar with unique pointer and shared pointer, you can make smart references now. You can have unique ref and shared ref, something that looks like it's on the stack, but is actually reference counted. Open some doors. We've got a way to simplify the pimple idiom, the compiler firewall pattern. So that pattern is used to insulate people from recompiles. It usually involves a whole lot of code duplication. You don't need it, or you don't need to do the duplication anymore. Just it'll forward everything through. And if you've particularly enjoyed this segment, which we've talked about some proxies, you can learn about something I did to make mixins with this, where you can add any functionality you want to any type you want at any point you want by looking up one of my other talks. I think it was the fundamentals of type-dependent code reuse. So if you like this, there is more. Now, if anyone's been wondering, what's the difference between this and inheritance? I think it's worth just briefly sketching. So we can extend any type that we want. I can extend an integer by forwarding to it with operator dot. What I can't do is inherit from an integer. And these are different powers. I have no way of stopping someone from returning my type from an operator dot call. There's no equivalent of final. And the last kind of interesting thing is a derived class knows that it is a derived class. It can call the base class's function. It can say, do the base version of this, or do that feature that I got from the base class. The wrapped type, when we're talking about an operator dot, so the int in our case, has no idea that it is being wrapped. And without going out of your way to do a whole new design pattern that kind of tells it that that's going on, there's just no way to do it. So these are different features, they have different powers, they're kind of similar, but not really. And that gets us to our last topic. Now, this is again stuff that you can take home and use right now. And again, it starts with a little bit of a history lesson here. I'm going to talk about compile time branching. And we've had a mechanism for doing this for a very, 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 very long time. My example here, default delete, standard default delete, it's in the standard library, comes from C++11, but you can write this code in C++98. And what it's doing is it's saying, hey, I've got a pointer, you tell me what kind it is with the template t, you could give me, let's say, int, you could also give me int square brackets to say, I have an array of ints allocated on the heap. And it figures out which delete operator to call. And the if statement works like this. It says, assume that the correct one is the top version, but I've got this specialization here where if it looks like it's an array, call the array version instead. This is an if statement. And if that doesn't bother you that this is an if statement, you've been doing this too long. This is magic. Right? This is arcane. This is something that is not obvious to beginners. It's not obvious to, I think, intermediates in the language. This is magic. This is why we have the term template metaprogramming that, causes people to hide in corners and dark alleys. We shouldn't like this. So let's just write an if statement as an if statement. And by the way, this works. I can say, if it's an array, do the array thing, otherwise, don't. This compiles, this is a perfectly valid implementation of this. And now my branch looks like a branch. I think that's awesome. Now, some of you might be saying, hey, there's still template metaprogramming hidden inside isArray. I'm actually okay with that. If you want to hide all of that in some very simple primitives that I can reuse, fine. But if statements should look like if statements in general. Another question you might have is, did I just introduce a branch at runtime? Is this as efficient as that version? And it is. Because if I give you any particular type t, let's say int, the if statement only goes down one side of that branch every single time for that instantiation of the template. And the optimizer is smart. The optimizer knows that you only do one side of the branch, and it just kills the other one. And if I want to do int square brackets for arrays, it makes a new instantiation, same thing happens. No branching happens at runtime at all. Awesome. Well, let's do something a little bit more complicated. I want to write a conjunction function, and that function says, given me any list of bools, do the logical and operator on them, return back that. And I can do this in C++11 with a constexpr function overload set. I say if you give me one Boolean, return it. If you give me multiple, do this pseudo recursion stuff that eventually boils down to that bottom case. And again, this deserves a magic hat because this is an if statement. Behold. Right? That's what an if statement looks like in the way we were expected to write this function in C++11. And that's kind of nasty. So welcome C++17. I can write this as an if statement. There's this new thing, if constexpr. I'll explain why we need the constexpr momentarily. And some of the magic has been taken away. Now, there's still variadic templates on the screen. I've got size of ... I'm not going to pretend that this is easy. But a branch looks like a branch. Right? That's a step in the right direction. If we got something like this in every C++ standard every 3 years, we'd be on a very good path. So again, we've got this pseudo recursion, figures out whether or not you have one argument or more than one argument, it does the right thing. But a branch looks like a branch. So why can't I just use if? What's the deal with if constexpr? If I write it as if, and I call it with my example here at the bottom, I pass it one Boolean true. Well, the bool b comes out to be true. The rest parameter pack comes out to be empty. And we take a look at our if statement. We're going to go down that else. That's what should happen, where we return that b. But an if statement, both sides of the if statement have to be valid with a normal if statement. And When I try and call conjunction with an empty parameter pack, so call conjunction with 0 arguments, there isn't one. So that's a compiler error. Right? That's kind of nasty. And I could fix that by adding another overload with 0 arguments, but we're back into magic hat territory. We're back to if statements that don't look like if statements, plus if statements that do look like if statements. It's even worse. So if const expr solves our problem. And the way it solves our problem is it only compiles the side of the branch that you're going to go down. So when we get to one Boolean, it says, who cares what's in the if side? We're only going to do the thing in the else side. That's what if const expr does for us. Now, some of you may have known your C++ 17 standard, what's coming pretty well. Maybe you've been sitting here wondering, why not a fold expression? Doesn't this just trivially boil down to this? And if you were thinking that, yes, you're absolutely right. The reason that this is the example I used and it can boil down is because it fits on a slide. If you want an example where if const expr really saves the day, and you can't just make it disappear by saying, you know what I mean, ... and these all together, try and write a compile time const expr find algorithm. Much harder. All right, so brief, why is this different from concepts? If const expr is about branching, it's saying do this or do that. Concepts are about constraining what your function accepts. It's about saying, hey, my function only accepts things that are random access iterators, nothing else. So they're related, they help each other, they're different. And I just wanted to call that out. Now, take this if const expr thing, and we can use it to do something awesome. There's this coin that was termed by Andrei Alexandrescu called design by introspection. It's where we say, is my type capable of doing something? If so, do it. And we can do this in C++. We've been able to do it for a very, very long time. But the barrier to entry, how big your wizard hat needs to be able to pull it off, that's getting better. And I'm really excited about that. So here's something from the standard library, Std Advance, where we've done this for a long time. Every standard library implementation that I know of does this optimization. What Std Advance does is you give it any iterator you want and say, please increment that n times. And every iterator can do this for loop, right? Every iterator has ++. They can all do that in O of n time. But some of them are random access iterators. And a random access iterator is basically a pointer. You can do constant time plus equal that same thing. So wouldn't it be great if we were able to write this function to say, if we have a fast iterator type, a random access iterator, do it the fast way, otherwise do it the slow way. This is designed by introspection. This is my type capable of doing the fast thing? If so, do it. Otherwise, do the slow and reliable thing that always works. And this is awesome. This is fantastic code. It works with any type you give it, and it's as fast as it can possibly be. This is something we should all strive for, that our interfaces are this nice. Now, there's still some template metaprogramming magic on here. There's the type traits thing that maps the set of all iterators onto the answer to the question, is this a random access iterator? I'm not going to pretend it's not complicated. But again, it's far less complicated than it would have been if we had to use tag dispatch back in C++ 14 or 11 or 98. All right. Now, I told you, you can do this in C++ 14. You can actually do it in 11 if you just change the lambda I'm going to show you into a function object. But I want to give you an implementation of this. Now, on the left, I've got just an example. On the right, we have the deepest guts of how this is all going to work. If we want to write if const expr as a macro, well, somewhere there needs to be a template branch. And the old way of doing that is with partial template specialization. So I've got a struct here. It takes the Boolean of is the if true or false, right? How did that evaluate? And a function to call if it turns out that that condition was true, right? What's the body of the if statement, basically? And there's two sides of my if statement here. One is we don't call the function. We don't do the thing inside the if. And the other, if the Boolean is true, you can see my specialization over there, then we will, in fact, call that function. Part 2 of this, because we're not in C++ 17 yet, and we don't have type deduction on constructors, well, I need to have my version of make pair. I need to have something that deduces the type of f. So the whole point of that function is just to figure out what type f is. That's all it does. The final piece of our puzzle is the macro itself. There's a condition, there's the code, we pass the condition in explicitly as a template argument, we let it deduce the type of this lambda. The lambda captures everything in scope by reference because an if statement, you are allowed to use the stuff outside, right? So we want things to be available. The magic of this is in that one little auto. So auto, in that context, is a generic lambda. Generic lambdas, basically all that's saying is, if you imagined this was a struct with an overload of the function call overload, well, now it's templated. And it's important that it's templated, because what we want is for when I write this code here, and I try and do plus equal on a type that doesn't support it, I don't want that side of the branch to be instantiated. I want that code to just say, oh yeah, we're not actually instantiating this template, so great, leave it alone, don't check it for semantics to make sure it's okay, because we're only going to do the else. Right? That's what I'm trying to do here. So we need it to be templated to get that effect. So auto there, and I could have written auto x, by the way, just an unnamed variable, says there's a template involved. And when I go to call it, I just have to pass it anything, something that instantiates that template so I can call the function. I chose to give it a bool, you could give it 5, you could give it whatever you want. And so there's if const expr in an older version of C++. You can write a branch that looks like a branch in C++ 11 if you do a few more changes. All right, so we've hit the end. So what did we learn? We talked about string view, and I mentioned string view has its issues, right? I think that as a community, we're going to learn a lot more about what string view means over the next few years. But the one thing I think people can agree on is that it is way better than const char star const for your global string constant. So start doing that now. That is going to save you some real bugs. It also is probably going to save you some performance. We talked about operator dot, and for me, that stuff's just fun. It's entertaining. I hope it was entertaining for you, that it gave you an idea of what the future could look like. It may not be that exact syntax. There's another proposal that does the same thing, but I hope you had fun with it. The last thing we saw today is about taking this wizardry, these magician's hats that only a few people have had, and trying to say, wait a second, we should make simple things look simple. We should open the door for every one of you to write functions that are as good as that one that said, do the fast thing when you can, and otherwise do the reliable one. And with that, thank you all for coming.
So the next word that you're going to learn, ladies and gentlemen, and again, I'd like you to repeat it loud and clear after me, is Isaacson. Thank you very much. Mark, will you be happy to take a question or two?
Please.
Okay, I'm pretty sure I need to show it to you and read it as well. So the question is, what does const expr mean? Is there a difference between this and just const expr?
Right, so all the way back at the beginning when we were talking about our string views and we made them const expr, why the redundant const? Or the potentially redundant const? They do different things. So const expr says evaluate this at compile time. Const says this value is immutable and cannot change. And in C++ 11, const expr implied const. In C++ 14, I believe they relaxed something that maybe meant that didn't that was not the case anymore in one particular corner case that I forget about. And then I think someone actually corrected me and told me I was wrong, and const expr still implies const. I wrote it for redundancy. If you write const expr, it'll be fine.
Question number 2, is that true that you're coming back tomorrow to deliver a talk called Developing C++ at Facebook at 1:35 p.m.?
Yes, Developing C++ at scale.
Oh, scale, sorry, there's a typo in the agenda. And question number 3, will you be coming next year?
We'll see. Time will tell.
Let me just reassure you that you just need slightly, not as many tickets from Berlin to Wrocław or Wrocław to Berlin. We can help with that.
It could be fun to double it. It could be fun to try and get 10 tickets, just to show you all how much I really want to be here.
That's how keen Mark Isaacson is. Thank you very much, Mark. Let's thank Mark Isaacson.
Thank you.